Hi guys, it's the Sciencebarbie. Today we are going to talk about eigenvalues and eigenvectors. Now here we have a 3 by 3 matrix B and we want to calculate the eigenvalues and the corresponding eigenvectors of this matrix. Now first step is to find the eigenvalues, and let's start with this. Now the first step are the eigenvalues. Start with this, and I'm going to demonstrate how this is being done. I hope slowly enough. Okay, now how are we going to find these eigenvalues? It's by using the determinant here of matrix B minus the eigenvalue lambda. This is what we're going to calculate, and we set this to 0. Now this is the equation system that we're going to solve. Now let's start with first doing here, that's what we want to know, the determinant of B minus lambda times I. Now I, you know how I looks like? The identity matrix looks like this. And if we multiply it by lambda, then we see the lambda is only effective here on the main diagonal, because only here we have non-zero entries. Now, here we start here with the first entry is 1 minus lambda. Correct, then the other two entries remain untouched here. Then we have minus 1. Here we have 3 minus lambda and 0. And then here in the last row we have 0 minus 3, and here we have 0 minus lambda is minus lambda. And we want this to be 0. Now let's calculate the determinant. Here it's just the product of the main diagonal, 1 minus lambda times 3 minus lambda times minus lambda. Now usually we would, extend the matrix here and apply the rule of 3, but we see we have lots of zeros here in the other rows and also columns. So if we, for example, look at this diagonal here, we see it's zeros, here we have zeros, and even if we look at the last one, okay, here we would also get, if we extend this, a 0 finally here. So this is all we're looking for. We're just multiplying here the main diagonal. Now let's do this. I would just start with this one here. We have 1 minus 1 times 3 is 3 minus 3 lambda. Okay, then here we are. Minus lambda times 1 is minus lambda, and minus lambda times minus lambda is plus lambda squared. Okay, times here, need to close the bracket here. Okay, here times minus lambda. Okay, now let's continue here. Let's start with lambda squared. We have lambda squared minus 3 lambda minus lambda is minus 4 lambda plus 3 times minus lambda equals 0. That's what we want to find. Now we see at first sight that the first solution for lambda 1, is going to be 0. Why? Well, product is 0 if one of its factors is 0. So we found the first solution for lambda 1 is 0. Now all we have to do here is look at this quadratic equation, and here we apply the midnight formula. It's called midnight formula because if your professor calls you at midnight, you have to remember it by heart. It says minus p half plus minus the square root out of p half squared minus q, and here we have p, and that's q. Okay, now lambda 1, 2 equals minus and minus is plus, 4 by 2 is 2, plus minus the square root. Okay, 2 to the power of 2 is 4, minus, and q here is 3. which means this is 2 plus minus 4 minus 3 is 1. The square root of 1 is 1. Now we have two additional eigenvalues. Lambda 2 is 1 and lambda 3 is 3. Now we have all, let's start also here that we have somewhere, lambda 1 is 0. Now we have the three eigenvalues, 1, 2, 3. Wonderful. Now we already found the eigenvalues. Now let's go to the eigenvectors. And I'm only going to demonstrate one eigenvector because all the other eigenvectors are done in exactly the same way. And just to save some space here and in the interest of time, I'm going to do only one eigenvector, and the other two eigenvectors are being done exactly the same way. So which one is probably the nicest one? Well, let's take this one. It's 1. It's very simple to calculate, right? So now let's take lambda 2 equals 1. This is the one that I'm going to take. Now, the formula is B, the matrix B, minus the eigenvalue that we already found times the identity matrix that we have here times the eigenvector is set to 0. Now let's start doing this. Okay, we have lambda is 1, so it's quite simple. We just do B minus I. Okay, let's start here. B minus I, 1 minus 1 is 0. This is 0, 2. We have here minus 1, 3 minus 1 is 2, and 0. And here the last row is unchanged until the last entry. 0 minus 1 is minus 1. And now we multiply it with a three-dimensional vector with its three coordinates x, y, and z. And this is set to 0. Okay, now what can we see here? Okay, now the first row, we can see it's nothing but zeros, so it's trivial. It says 0 equals 0. We're not going to use that. We're going to look at the second row here. It says, so we multiply the second row here with the vector and we get 0. So it's minus x plus 2y plus 0z equals 0. Now let's see how x would look like if we put the 2y to the other side and multiply by minus 1. We got x equals 2y. And now let's look at the third row. We have 0 times x. Okay, we're not interested. It's minus 3 times y. It's minus 3y minus z equals 0. Now let's look at z. If we put minus 3y to the right side, we got minus z equals 3y, but we want z, so z equals minus 3y. Nice, isn't it? Now we can choose any value for y. Now let's say choose y equals 1, because that's a simple value, right? Then we got x equals 2 and z equals minus 3. And the first eigenvector b1 equals 2, 1, and minus 3. Okay, maybe let's quickly look at the second eigenvector because I still have some space here on my sheet. Now let's look at the 0, 1. So lambda 1 equals 0. Let's do this one really quick. It's not that bad, right? Because if I multiply here the identity matrix by 0, it's the 0 matrix. So all we gotta do is write down the given matrix B. Okay. It's 1 minus 1, 0. It's just the matrix that we had given right from the start. 0, 0, 0. And we multiply it again with x, y, z, the eigenvector, and we set this to 0. Now let's have a look. Okay, the first row says x equals 0. Can you see this? X, if we multiply this through, it says x equals 0. It's already one solution here. Nice, isn't it? Now let's have a look at the second row. We have minus x plus 3y, minus x plus 3y equals 0. Now that x is already 0, we have 3y equals 0. Now y always is also 0. And again, in the last row, we have 0 times x minus 3 times y and 0 times z, okay, equals 0. Now, looks like this, 0 times z equals 0. Now we can use any value for z, for example, 1. So at least so we choose z to be 1, and our second eigenvector is then 0, 0, 1. Okay, can't be the 0 vector. And the last lambda for lambda 3 is 3. Just give you the result. If you want to do this on your own, you may do so. Now the second one, or this third eigenvector b3 equals 0, minus 1, and 1, and it's being calculated exactly the same way as the other two eigenvectors. And what do we get in the end? In the end, we get 3 vectors that help us find a basis for a new coordinate system. So what we do here is we have this matrix, and somehow this matrix is doing something. So we can multiply any vector in a coordinate system by this matrix, and something happens to the vector. It's being stretched or being shortened. It could be rotated. Okay, so it could be, transferred somewhere, and this is being done with all the vectors in a given coordinate system, but the eigenvectors. Now, if we look at the eigenvectors, whatever we do, if we multiply these eigenvectors by this matrix, so if we apply the matrix to these eigenvectors, nothing happens to the eigenvectors. They stay exactly the same as they are. So there is something very characteristic to a given matrix.
Das war ein Mathematik-Tutorial der Sciencebarbie. Jedes Like und Abo des Kanals freut uns sehr. Für Feedback und Kommentar nutzen Sie die Kommentarfunktion.